Today's lesson is on colligative properties. What does colligative mean? It's a property that is affected by the number of pieces that are dissolved in the solution, not what those particular pieces be. So, in other words, it doesn't matter whether I dissolve sucrose or glucose into water, so long as I put the same number of molecules, they will change some properties of that solution in exactly the same way. Some examples of colligative properties: vapor pressure, boiling point, freezing point, and osmotic pressure. So let's start with vapor pressure, because understanding that is key to understanding how boiling point and freezing point are changed in a solution. So first of all, what do we mean by vapor pressure? That is the pressure that is exerted at the surface of a liquid as it starts to evaporate. The vapor above the liquid, that gas, is pressing down on the surface, exhibiting some sort of pressure referred to as vapor pressure. We are going to limit our discussion of solutions to solutes that are considered non-volatile. That means only the solvent will be evaporating from the solution, not the solute. So non-volatile solutes do not add any vapor pressure above the solution, because they are not able to escape. So how is vapor pressure affected? It is always lowered after we add a solute. And we are going to look at a picture to illustrate why that is so. So in our first flask here, we have pure solvent. Let's assume that our solvent here is water. So we have liquid water, and at the surface, we will always have some water molecules that are evaporating and escaping into the air above it. This vapor pressure would be the pressure exerted by these molecules above this surface, pressing down on the surface. And this gauge here is reading at a 3 for our pressure. Notice what happens in the second doer there, where we are adding a non-volatile solute. A reminder, the non-volatile solute, represented by the yellow molecules here, means even though they are dissolving, they are not going to evaporate. It is only the water that is volatile and escaping at the surface. If we compare the two pictures, we can see that fewer water molecules are able to escape at the surface in the solution. Why is that? It's really because this non-volatile solute, they're getting in the way of the water molecules at the surface, and so fewer are able to escape. So they kind of act as blockers. So what we will see is that in any solution, when I add a non-volatile solute, I will always lower the vapor pressure. We are going to see that understanding this fundamental concept that vapor pressure is lowered in a solution is key to helping us understand what happens to the boiling point and the freezing point of a solution. Let's look at a curve of vapor pressures for a solution and for a pure solvent. The blue curve here illustrates the vapor pressures for a pure solvent. In this case, they're using water. Our upper curve is the vapor pressures between a liquid and the gas, so this whole line would be boiling points. The lower curve represents the vapor pressures between the solid and the liquid, meaning this line represents freezing points. So our blue curves are for a pure solvent, water. Because we know that addition of any non-volatile solute will cause the vapor pressure to drop, we see that this red curve represents the vapor pressures for a solution. Notice it is lower than the blue curve on both ends. So we are saying that addition of a non-volatile solute will cause the liquid to have a boiling point elevation or increase and a freezing point depression or drop in the solution, simply because in both cases the vapor pressure was lowered. So it sounds like we're contradicting each other, but let's look at the curve closely and see why this makes sense. So here, the vapor pressure indeed is lowered all the time. So we have this curve is lower than the blue one, and this curve here is lower than the blue one as well. So now if I start asking about the freezing point for the solution, a reminder, these two lines are representing freezing points. As I start coming across my axis here, I hit the solution curve before I hit the pure solvent curve when I am looking at the freezing point. So the freezing point for the solution is lower than its pure solvent. As I continue to move across, I now hit the pure solvent curve for boiling points before I hit the boiling point curve for a solution. So that means I'm going to always have boiling points that are higher for solutions. And we use the term boiling point elevation for a solution, freezing point depression for a solution. So how can I calculate the boiling point and freezing point for a solution? What we actually calculate are the changes. So we'll say delta T, meaning the change in the temperature for the freezing point, little FP, is equal to M for molality times a freezing point constant. For boiling point, again, we would measure the change in the boiling point. It is also equal to molality times a constant for the boiling point. The K is dependent upon the solvent. So I will look at a table and pick K, simply knowing what my solvent is. It is a different value if we're calculating the freezing point than if we are calculating the boiling point. The other thing that we have to tune into is the kind of solute that we have. If it is a molecular solute, it dissolves, but each of the molecules stay together. So whatever the molality is for the solution, we don't need any adjustment. However, as we have previously discussed, if I have an ionic solute, that ionic solute breaks into the individual ionic pieces, meaning that if I have a 1 mole solution of an ionic compound, I'm going to have to adjust it based on the number of ions that are present. And so our equation above, we will add an I for that correction if we have an ionic solute, right? And the freezing and boiling point constants are not something that you memorize. They are something that we look up on a table. So we are going to limit all of our discussion to the handful of solvents that are listed in this table. So what we will need to be careful of is reading the solvent. So for example, if it's water, we would be looking at this line here. If we have benzene, we would be looking at this line here. The boiling points are given because, a reminder, we're going to calculate the adjustment to the boiling point. So if we find that the change in boiling point is 5 degrees and it was in a water solution, we would add 5 to the original boiling point of water and find its new boiling point. The individual Freezing point constants for boiling and freezing are in the appropriate column. They have units of degrees C kilogram per mole. And again, notice that the value is different for each solvent. So I have to pick my solvent and then tune into whether they are asking you to find a boiling point or freezing point, so that you know whether you want to be looking at this column here or this one over here. You will need this table as we solve some example problems together in our next video.